Hello, my name is Igor Litvin. So I currently represent Technical University of Munich. I work in a group in Janis Nötzel. So our lab is actually quite new, approximately 1 year old. That's why we have some results. However, it's possibly not so exciting. However, it's still quite interesting. We're trying to publish some work. Today, I will speak about photonic processor. And our main idea of why we bought this, we actually bought two photonic processors to use it like encoder and decoder for communication systems. So what is photonic processor? This I make a couple of pictures for you. This is what we see inside. This is silicon nitride based integrated chip. It's approximately size like 1 centimeter, 1 centimeter by 1 centimeter. This is box which we have, and this is scheme of our photonic processor. This is 8-mode photonic processor. We have 8 inputs, 8 outputs. So we have also 16-mode photonic processor. And why it's interesting to use? Actually, by this photonic processor, we can decompose almost any unitary matrix 8 by 8 and use it like a matrix multiplier. So we have input states, then we can decompose any unitary matrix, and then we have output space will be like multiplication of our input states by our photonic processor. In our case, our photonic processor consists of 28 such unit cells. So this is a line, blue line, it's represent like Mach-Zehnder interferometer, and red line represent like outside phase shifter. Transformation of this unit cell represented by this matrix transformation. And now this is idea to use this like a coder and decoder. We bought this photonic processor and tried to use it, like I said to you, and we found a lot of problems. And about these problems, I will try to explain you how we sorted out these problems and how we can use this photonic processor for signal processing and for joint detection. So first problem you immediately can identify here. So what I said to you, look at this. This is a transformation which must perform. This is our every single unit cell. However, it's in ideal case. Of course, in reality, it's not like this. In reality, this picture here, I represent what we have. This is dashed curve represent analytical results, and this is solid curve represent what we have in reality, in experimental. And sometimes we can see immediately some interesting point. So at 0 point, this is MZI phase. So at 0 point, when we have 0 phase shift, so we have almost 0 error. It's quite okay, and then pi as well. So in these 2 points, we call them bar and cross points. We can use this photonic processor almost with no problem. This is why we cross and bar. So bar setting, it's when this MZI phase shifter in setting pi. In settings pi. So it's if we have input 1, so output also will be 1. Or input 2, or output also 2. Cross setting, it's for MZI equal to 0. So this is phase shift equal to 0. We have a 2, output 1. In this region, yes, no problem. However, in this region, pi over 2, we have huge problem. But in general, if you want to decompose any unitary matrix, of course, we have to use whole region. And inside of this region, sometimes you have like error of 10%. And you can imagine if you have a chain of such unit cells, of course, this is error will be multiplied. And on the output, we cannot trust our output in this case. So what we can try to recalibrate our photonic processor. So how? So for this, this is idea like this. So because we can use actually bar and cross settings, this is no problem. So by using bar and cross setting, we can deliver our beam, for example, from input 1 to any of MZI. For example, this MZI 16 we deliver, change our phase of this MZI, read your output power, and compare this with our analytical equation. And then as soon as you compare, you will see this error, and this is I represent here. So this is analytical equation. This is what we have and then you can save this information in specific file. And then when you in future will use this setting, you can apply this error. So this is and such way, quite easy way to recalibrate we perform, and this is result. So before recalibration and after recalibration. And you can see we have quite dramatic improvement of our error in comparison to analytical equation. And this is how looks error before and after. So blue line, it is before, and red line after. And here also dashed, and so we can see quite nice. However, this is everything for MZI. But unit cell also has an external phase shifter, which also must be calibrated. And this is a bit problem. So this is recalibrated MZIs. However, how to recalibrate phase shifter? Why? Because if you look at this equation, so phi, this is our change, this is sitting here and sitting here. If you change this phi, you actually will not able to change any intensity. So you changing phi from 0, so actually for external phase shifter from 0 to pi, but intensity, you will not see this difference in intensity. That's why it's difficult to recalibrate it. For this, we sorted out this problem by creating so-called effective MZIs. So yeah, so we created like a scheme here. This is kind of effective MZI. So it consists of actually 4 MZIs. 7, 7, and 14 MZIs in setting 50 by 50, so it's pi over 2. And then is 2 MZI in the setting, in bar setting. In this case, and now we're able to recalibrate a phase shifter 76, which actually external phase shifter. And now we have actually intensity modulation, and we recalibrate it, and this is result. So this is a result which we got for recalibration of phase shifters and MZIs for full photonic processor or 8 by 8. And you can see this is on, in reality, before, this is orange, this is what we had before, and blue, this is what we got after. Approximately, in average, we decrease our error like 3 times. Okay, will it help or not? We can see on this picture. On this picture, what we done. So we have single input number 3, we send laser 1550, and then we use red array to decompose 8 by 8 Hadamard transformation. So we decompose this array like of 4 by 4 matrix, and this is phase shifts which we have. And what we expecting, we expecting equally redistributed power after such decomposition. And this is result before recalibration, and after recalibration, we can see quite significant improvement of equality of all signals. So yes, recalibration works. However, it's first problem we sorted out, but now we have a second problem which is much more difficult to sort it out and much more critical. And this problem we can see here. If you look at photonic processor, it's quite small. It's like less than 1 centimeter, 1 centimeter by 1 centimeter. However, this photonic processor consists of 56 phase shifter. This is actually thermo-optical phase shifter. So actually, this is heater. So we have 2 electrodes which heat area around the optical fiber, integrated optical fiber, and change refractive index. So average, what we have approximately 300 milliwatts for every single phase shifter. In average, for full photonic processor, we have approximately 10 watts of heating. So what is 10 watts of heating? So if you use laser, for example, 1 watts, you already able to feel it by hand. So 10 watts is quite seriously, and actually this is the 10 watts we have only on this is small area, and quite important to understand that we use thermo-optical phase shifter. That's why temperature we must hold constant because we calibrated for specific temperature. In our temperature, in our case, it was 20 degrees. So in this case, how to hold this temperature? We use quite serious water cooling system. So and 3 fans, quite significant fans, and because we use 3 fans, these 3 fans create quite serious airflow inside of this photonic processor. So, and we see this is to this photonic processor, we connected 8 optical fibers. So actually, this 8 optical fibers constantly shaking. And if you, at least sometimes work with multimode, for example, fiber, and try to shake multimode fiber, you see this output of multimode fiber, this is speckled field. And actually, when you shake this, you can see quite huge jumping in speckled field. And this is in this situation, we also have the same situation. So we have to sort it out because of output of such photonic processor actually completely random. And how we can sort it out? We can try to use feedback control. So firstly, we can measure this. So in order to measure, we propose to use interference scheme here, which I represent. So we have a laser field, a laser beam, then we split in two and let them interference. So directly from a laser. And then with this is splitting, we also propagate through photonic processor and also let them interference and try to compare what happened before and after photonic processor, what happened with the field, what happened with phase. I have problem with my video, but it is actually our interference stripes, which quite seriously shaking after photonic processor. And this is picture represent our results. So red line, this is what we have phase stability or instability before photonic processor, and blue line after. So we can see it's quite serious jumps. And so how to sort it out? So one of the way to sort it out, it's use feedback control. So we propose such scheme of feedback control. We are quite lucky because photonic processor actually has a lot of phase shifters.
But the question, why can't you make it equals out?
Yeah, we did it. So actually, yes.
Why can't we change the
we did it. So we open this. We glue this. We put. However, it's not only airflow. It's also shaking itself because of we have a water cooling system. So actually, this is mechanical movement inside and plus vibration. So it's quite complicated case because we have two of them and they must connect to each other. So we have a double problem because we will try and actually communicate between these two photonic processors.
So again, about the fluctuations, because I try to understand it, it is already coupled to the chip from the fiber. Right?
Yes, it's
coupled. And then why we have fluctuations?
Yes. So we have, for example, 8 fibers, which are actually shaking. So distance, when you shake, but they shake it independently.
No, but at the end, they will be glued to the waveguides. So
yes, they glued to waveguides. However, they shake independently. If you will shake, for example, if you have a single multi-mode fiber, yeah, and you just shake it like this, a bit, so your output field will be completely out. Yes, multi-mode fiber, it's worked like this. I worked like 10 years with multiple fibers. So it worked like this. Look, so you have multi-mode fiber, for example, 100 modes inside. So you bit shake it. And you have speckle field here. And you can see speckle field will be completely, your speckles will be start to shake like this. It's approximately situation like this. So you feel like, so because of its couple, so we're not changing distances, yeah? So phase must be stable, but it's not like this because we have stresses. And really, this is, phase is actually extremely sensitive. Because of these stresses inside of optical fiber, different stresses for different fiber, this is difference creating this instability. I will show you later how it looks.
We can discuss offline this picture. I mean, from the fiber fluctuations, right?
Fiber fluctuations,
the coupling that
coupling stable. Even what he said, we try to make it as stable as possible with company who produce this. No, it doesn't work. Okay. Okay, so we propose to use such scheme. So what you see on the scheme? So yes, we quite lucky because of photonic processor actually has phase shifters, a lot of phase shifters, which we can use to control phase and actually use it like a self-feedback control. So use this one of these phase shifter to fix our phase difference. However, we have to somehow measure this phase difference, and this is firstly scheme propose which we can measure phase difference. So we use phase shifter, one phase shifter, 2 inputs, for example, phase shifter 25 50-50 beam splitter, and output 1 and 2 at 1 and 8, like a amplitude measure, fast measurement power meters. And by measuring this power difference, we can actually identify phase shift, which we have to apply to correct our phase. So we can, so this is equation, this is which I show. This is amplitude, depends on phase shift between these two inputs. Okay, so this is such idea. We just constantly repeat this loop, and we could quite lucky because of photonic processor. Actually, this is not really a thermal optical phase shifter. They're not really fast. However, it's around 1 kilohertz. However, our rotating actually speed approximately like 20 hertz. So actually, it's much faster than our phase drift, let's say. So in this case, firstly, what we can do, we can firstly make a proof of principle or calibrate it. So use one input, divide our beam on two. Use one of MZI like 50-50 beam splitter, divide on two, then use one of the phase shifter like random phase generator. So just completely random, every 10 seconds I completely random phase and try to control, try to by reading this is output 1 and 8, amplitude, try to control it and try to fix it. And so this is successful. And then after we try to perform real feedback control and try to fix our phase modulation, and this is result quite nice because of we in this case we also use two inputs, so two shaking inputs, and use phase shifter 2022. This is the picture show first picture. This is output 1 and 8. This is for our amplitude before and after feedback control, so switch off, switch on, and here, so here as well. So this is on this picture we try to produce Hadamard transformation inside of this region, left region, and we see so before 60 seconds we see quite unstable picture. So this is how we, if you will buy photonic processor and try to perform Hadamard transformation too, this is your results before what you could expect. And this is after 60 seconds, we switch on feedback control and we have quite nice results and stable. So, okay, cool. So we also check it for quite long period of time. It's approximately 6 hours. And during 6 hours, we have stable output. No problem. And now this is only for 2 inputs. However, we have like 8 inputs. How control 8 inputs? So now we have to somehow make them equal in phase. So, and this is our scheme which we propose. For this is not for 8, for 4 inputs. So what we're trying to do? So we have a input 1, 3, 5, and 7. So and we're trying to equalize phase between them. So how? Half of photonic processor we use like feedback control outputs. So if to analyze your phase and make a feedback control. And half of photonic processor we're trying to use like a signal processing. In our case, this is Hadamard transformation 4. And 3 phase shifters we use to control this phase and to adjust phase to one of them. For example, input number 1, it's free input. So it's completely a free fluctuation. But input number 3, 5, and 7, we're trying to feed input number 1. And in this case, we have a quite stable signal, and this is our result. So firstly, what we done, we made a simulation. We able to make quite nice simulation where we quite nicely can. So sometimes it's difficult even to distinguish between our simulation and experimental results. So we quite nicely able to simulate noise in our photonic processor using Brownian motion model. And this is a results. So the results before 20 seconds, this is no feedback control, and after 20 seconds feedback control and producing Hadamard 4. And this is 2 results and quite interesting situation in a phase situation. So we can see before and after phase. So after 20 seconds, we have quite nice fitting all this phase in both cases. And now let's see how it looks actually experimental results. Experimental result looks like approximately like this. So this is a transformation of Hadamard 4, 4 inputs, completely free fluctuation in a phase. And before feedback control off and feedback control on. So we can see this is actually results before like I think 18 seconds. This is output which you can expect when you buy such photonic processor and you just switch on and try to make Hadamard transformation, and this is what we will have. And then this feedback control, it's quite nice, a bit noisy, but we work on this. Right now it's a bit better. So, okay, and now question following. Okay, we able to produce quite stable signal processing by 4 inputs with photonic processor. Now, our goal is not like this. Our goal is create communication between 2 chips. For example, create like a some kind of joint detection. Is it possible or not? Because of joint detection, for example, if you're trying to produce joint detection, so we have a code words, and every single code words, how we control these code words. So actually we change in phases, 0 pi, and quite important here, we also trying to actually fix this 0 pi. So we're trying to fix phase modulation. And this is sometimes it is a quite serious problem can create. So this scheme. So why it's also quite interesting. So why we use Hadamard? It's quite interesting situation for Hadamard we have. You can see this is Hadamard code words 1, 2, 3, 4. And if we have, for example, Hadamard code words 1, all inputs, so all power go to, so you see decoding in output number 1. If Hadamard code words 0, 0, pi, in number 2, and so on. So actually, it's quite interesting. It's like we have an amplification. It's quite interesting situation. So we have it's like with joint detection, we not only like receiving signal, we amplify signal. If we will have for example, Hadamard 8, so we possibly able to amplify it like 8 times. So this is quite interesting and useful situation. This is why we're trying to sort it out. And this is idea. And let's see, are we able to use the same feedback control plus our calibration to make joint detection? And this is a first attempt to make it, and this is quite successful. So we see this is results before. So we sequentially change Hadamard code words before step feedback control and stabilization in phase, and after stabilization of phase. So we have 1, 2, 3, 4. So this is outputs. We see amplification of our signal, and we see quite clear and able to read our code words. So yes, this is it. So if you're interested in our work, of course, you can go to our publication and read, and plus we can be happy to collaborate and speak in future.
Oh, thanks a lot. And, you're doing the real hard work, like proving the theorems is easier sometimes. I have a naive question. So when you do the feedback control on the receiver side, how do you make sure you're not compensating for the phase that you're trying to measure?
Yeah, that's why I said. It's quite it's quite challenging, yeah. So exists a couple of ways how to do this. Actually, we don't. I don't want to say exactly way because of we trying to patent this.
Okay.
So, but way firstly exists. So actually, changing of code words is really fast. You can change. You can change it like gigahertz speed. However, feedback control itself is slow. So actually, this is phase fluctuation slow. Why? Because of we have a fence which rotates like 20 times per second. So we measure approximately like spectra of this is a mechanical movement. It's maximum approximately 40, maximum 100 hertz. So for us, 100 hertz, and in comparison to gigahertz or megahertz, it's much slower effect. In this case, when we jump in code words, so actually, we not see any problem with the second part of our measurement, where we actually not a measure, where we make a feedback control. So answer like this. And exists second way also do this, because of we actually not able to change with gigahertz right now, because of our photonic processor quite slow. Honestly, it's able to only change phase like a 600 hertz, 700 hertz maximum. So in this case, we have a second way, but I will not say it right now. So exists a second way.
I mean, I had similar issues 20 years ago when I was working on a CVQKD system. And in the end, we were sending a lot of pilots because the phase was fluctuating slow enough. So we could compensate with a lot of pilots. And, in the quantum case, the rates are so low anyway. The penalty you pay by using pilots, that was enough to compensate for the phase fluctuation. My last question is, what's your target visibility, say, right? I mean, like, usually you want your interference to be as clean as possible.
Mhm.
And so especially if you want to operate at lower power and whatnot. So do you have a target visibility that you're trying to achieve?
So you mean like error which we trying to achieve and we happy with this error?
So, I mean, if your goal is just to do communication, maybe you have a bit error rate in mind. I mean, you could do like an eye diagram and evaluate what you have. No, I'm thinking about just the fringe visibility, right? I mean, Vmax minus Vmin over Vmax plus Vmin. I think that's typically what you use to measure the quality of your interference pattern.
Yeah, so actually right now I cannot say you exactly. So we don't have what you said as such goal. We're just trying to make it as good as possible, let's say like this. So as stable as possible. Our problem here not only with our interference is also with we have quite a lot of noise from a detector and some from communication. So this is other story. But yes, we don't have right now. We're just trying to make it as good as possible. Also, I want to mention to you the following. That's what we also saw in our measurement, even 3 times per second phase correction already okay. So we made some experiment. We published this. So where we only try to make it like a 3 times. We switch on like 3 times per second, like once only, but make nice full corrections. And it also was quite okay. So in this case, I can even, in your question, for example, how we can distinguish. So we also discussed it. So we can only inside of this, when we correct it, we can stop it. And then we correct, and then we carry on. Correct, carry on. So 3 times per second. So it's quite easy for us, let's say, to correct it. However, as soon as we go to more complicated situation, for example, chip 16 mode, so like a decomposition of 16 by 16 matrix. In this situation, of course, it will be much more challenging because we have more and more uncorrected phases, and we actually quite challenging. So it must be quite serious speed to correct all them together. So connect them and correct them together. So it's not only one stage; it's actually this sequential. You correct. So yeah. So in this case, it definitely in future it will be a problem.
That was actually a very good question, I think, because this we did investigate from a theoretical perspective whether there was going to be a scaling issue. Yeah, like you said, it needs to work first.
Great talk, madam. I have a very similar question as Matthew's, but more of us maybe a suggestion. Perhaps one possibility is that you can ask yourself if you wanted to achieve, say, super additivity. That's another metric you can say with a 8 mode or a 16 mode green machine. Then as you turn up your phase and stability, with your feedback-based control, what is the tolerance up until which you still get super additivity? So that could be one way to quantify it. Yeah. But of course, there are other different applications of this too that you could benchmark against.
Thanks a lot. So, like I said, of course, so we need such help because we, like I said, only 1 year ago opened our laboratory. We actually start to work with this 1 year ago, and 1 year ago we still even didn't know what happened. We just switch on, trying to make a communication between 2 chips, make a, like I said, green machine based on your actually work, and then we see it like it doesn't work. And then slowly we will come to solution. We contact company. They looks like we don't know. They said they don't know anything. Okay, and then we start our journey, and this is journey now come to like 5 publications. But yeah, so but anyway, we extremely extremely young team right now.
Well, thank you for the interesting talk. I must have some technical questions. So you said did I understand correctly, you're using multi-mode fibers?
No, single-mode fibers. I just explained about multi-mode fiber, but this is single-mode fibers. 8 single-mode fibers, yeah, which...
So you just get the intensity fluctuations because the coupling...
No, coupling, okay. Quark, like we discussed, coupling 100%. The null is like solid. However, shaking itself creates stresses
Yeah, so coordinate means basically you get some sort of polarization dependence on what the steps.
Yeah, polarization also. So of course, this is other story about polarization and our chip and how it connects to polarization. So our chip, I think it's only can propagate like horizontal polarization. So it's actually cutting a vertical polarization. In this case, like you said, as soon as we introduce some, let's say even variations, I can say, because of as we actually moving. So it's in this case, we change a bit polarization, of course. So of course, it's also kind of problem. And this is in this case, we will have not a problem with phases, we will have a problem with intensity. Because as soon as we change polarization and only one polarization can so we cut in actually polarization. In this case, Hadamard transformation will be not really good because for us, it's also a problem. So this is what we're trying to make. Yeah. So, and yes, to your question, yes, we have problem with polarization sometimes, but it's not so difficult. Like,
but what is the main problem then? I didn't understand that.
The main problem of as soon as so fan works, everything shaking. So
yeah, that was actually the second question. Why is the fan next to the bucket? I don't understand that.
Yeah, this is.
I would just honestly, it's just like
this is a fan actually not really close to this. Honestly, they trying to avoid it. However, it's a full box itself. It also a bit shaking. So altogether, three fans, quite huge fans actually. It's like this. So all three fans plus optical fibers, which and shaking.
Yeah, I mean, I understand. If you look at my talk tomorrow, you will show you also a little bit of, because we're doing engineering for entangled photon sources and racks and so on. And you have also the kind of vibration problems, obviously.
Yeah.
And if I see that, I would immediately change the system, right? Because that.
But you have to understand. So, okay, let's assume we fix this problem. Yeah. Let's assume we don't have this problem with this chip. Anyway, we have 8 optical fiber. Yeah, which separated. And they, for example, propagated somewhere. So, of course, you will have vibrations.
Yeah.
So anything, for example, U-Bahn or something like metro, how you call it here. It's like buses moving, everything moving. So anyway, you will have this problem with phase instability. You actually use it.
I think it.
And you can use it.
Case test bed that may be good, but I think the changes were probably much slower on much different time scales. So let's say. One thing we are doing is basically want to stabilize links between, let's say, our quantum systems, which are maybe going outside or in uncontrolled environments. And you get basically problems with, let's say, the sun is shining, temperatures rising, and you get changes over the day, but these are much slower.
I don't think this is slower. Honestly, look, if you have an optical fiber, like let's say optical fiber, 100 kilometer or 200 kilometer between, for example, Munich and Berlin, we're trying to make a communication.
Yeah.
So of course, this is not really slow. So it's all together somewhere in one city, somewhere in this, like it's all together. It creates some vibrations, and it will not be like really slow. No, it will not like this. It's actually create, and I think somebody here has like Janis has experience with this. So, and I never did it, but I think it will be quite.
Experiments in Stuttgart, we measured the fluctuations in an intracity loop, saying 35 kilometers or so.
So this is what a really good question. This is what we're trying to do right now. So we have one publication which I don't describe here. So what we're trying to make, like get a spectra of movement spectra of our fluctuation. And ways maximum minimum. So what we're trying to do now, we know we have access to some optical fiber with a couple of kilometers in Munich. And so we want to connect to this optical fiber and measure the spectra. So vibration spectra. In this, as soon as we will measure this, how strong it is. In this case, we can firstly, what we're able to simulate. This is quite important. And then we can see how also we have to add this fluctuation to our simulation. So because of this firstly, we have 2 vibrating photonic processor plus vibrating fiber, which actually is. So it's quite a difficult situation.
Just from the concept, if I would design this kind of system, the way I would do it, water cooling, is good because you can transport a lot of heat. I would put the water heat exchanger directly below the chip, glue it on there, and I would not use air cooling in this sense. That makes no sense.
But this is air cooling. As I said, it's extremely a lot of sense. Why? Look, we must hold our temperature exactly 20 degrees. 21, 22, it's not okay. Why? Because of we use a thermo-optical effect. So actually, it means like we have a heater, we heat an area around of optical fiber, integrated optical fiber, in changing refractive index. So
But I'm saying that the water cooling is much better at that. Much better.
Yes, but water cooling, this is mechanical movement as well. So it exists.
You can just put a plastic tube in a sandbox. You have completely vibration.
Yeah. So honestly speaking, possibly you will be better engineer. I'm not engineer of this system, of course. So you can open company and sell better photonic processor.
Maybe look if you talk after my talk tomorrow, because I have exactly this kind of engineering challenges, right?
Great. Sure. Thanks.
So I did not catch the algorithm part of your the feedback control very well. So can you tell me something more? If you're depending upon the unitary that you're trying to implement, does it work faster or slower? Like for example, if it's something as simple as a Hadamard versus something more complicated, does the feedback control algorithm work faster if it's easier unitary or?
Yeah. So it's completely independent.
Independent. I see.
So our transformation, and so we divide constantly our chip on two parts. First part, it's transformation part. So it can be Hadamard on any like a Fourier any transformation.
Yeah.
But then second part of chip, they independent. So second part, feedback control.
Yeah, the feedback control. But it was on the one chip that you showed. Right? The top part was feedback control and the bottom was yeah. So
I can explain if you want. One more time?
I see. Yeah, could you just go to that slide very
Yes, of course.
If there is time, sorry.
So for 8,
it was that you had a top. This one, exactly. So,
yes, this is. I can explain it.
So the whole thing is one Clements mesh, right? And so you have the bottom part is doing your Hadamard, the unitary.
Feedback control, Hadamard, yeah. So we have what we have here. We have 4 inputs, yeah?
Yes.
We split beam of energy of 4 inputs on 2. First one go to Hadamard, second one go to feedback control. By feedback control, we measure actually our phase difference between, so what kind of phase difference we have between input 1 and the rest of them. So with all of them, we're trying to fit input 1.
I see.
So that's why we use 3 only phase shifter, not 4. Only 3, because of one of them free. So input 1 free, 3 of them, we try to feed them. Okay, so this is this part. In second part, we use, actually I didn't say because of I had limited time, we use also phase shifter 22, 26, 20, 30. This exactly the same phase shift which we use here. So for this one, because of this one, we use to control and exactly the same for this part.
I see. Okay.
Yes. So scheme like this. So in this case, in your question, so they independent, and it doesn't matter what you doing here. This is completely any transformation you can make. The speed doesn't change.
So you're basically probing every pairwise phase with your probe side, and then you're correcting for it.
Yes.
I see. Okay.
Yes. This is what will happen with phases in the last picture. So before phase is completely independent and kind of random. And then after, they try to fit each other. All of them. So one of them free, is, as I said, it's number 1. And the rest of them just trying to fit it. Of course, if you will have a bigger processor, we trying to make it on 16-mode photonic processor. You can already like stabilize 8 inputs and make 8x8 matrix stable. In this case, it will be like a bit slower, of course. So you need more iterations to control it. But yes, it will be also 8 modes, which must fit one of them like this.
Sorry, thank you for the talk. And but I also have a comment. Let's say for me, like these, especially these plots are totally in the dark because I don't see what I should see there. Like because you see, like on the left hand side, it seems to be noisy. On the right hand side, it seems to be more flat, so to say. I don't get the like in your measurements, like you cannot differentiate between the actual MMIs which are in there, like the beam splitters, and the quality of your chip and your feedback loop. So what I would be interested in is a frequency spectrum. So like this is a time running here. And I think, let's say, Mathieu did very decently. I would say, like in this problems, you have to move away from DC measurements, which are, as I said, like I don't see any value in these.
Yeah.
You have to go to beating lasers, and you can analyze quickly, like exactly the full swing in your interference, and then you know everything. You pull it out of the DC measurements, because this is something which always will limit you.
Okay, firstly, I understand you. About spectra, yes, we have it. I just didn't present because I need a lot of explanation. Like as discussed right now, so we have full spectra before and after feedback control, and how spectra change, vibration spectra of actually vibration spectra. So we have it. So I just represent because it's a bit out of here. Rest of what we see on this picture, this is what we need. So this is outputs with Hadamard 4 before and after. So Hadamard 4, how it works, equation I already showed before, this one. So this equation here possibly. So if you have 4 inputs anyway, so what we expecting in one of input all power, and the rest of input 0 power. This is exactly what we got in this, for example, this one, and this is in our experimental result, exactly what we have. Firstly, and secondly, what I also want to show this experimental result fit exactly simulation as well. And this is what we have. This is experimental result for Hadamard transform. You see quite clear what we have here, and see on here also quite clear that we have exactly the same outputs. That's why I presented like for audience just to show this is experimental simulation and our idea work. However, yes, you're right, of course. It will be nice to see spectra, vibration spectra before and after. We have it. We have it. So actually, we published it half year ago. So it's looked like understandable, and we definitely decrease our vibrations in when we switch on feedback control. Thank you.
Okay, so if there are no more questions, then let's thank Igor again.